Okay. Okay. Let's get started. Okay. So we learned about the basic of memory systems in the previous class. So we will learn about the basic of caches. So so what is a cache? Okay. So actually this is a computer system terminology. Okay. But so it's also normal English word. Okay. So what is the definition? So actually, in the normal in a normal case, cache defines a hiding place. Okay, but so this is not the meaning of a cache in a computer system. So you can check this one, the computers. So what is a cache? Cache is a temporary storage or space or memory that allows fast access to data. So we can focus on two words, a temporary. Okay, it's a temporary storage. It's not a main memory. Okay, so we can store our data in the main memory, but cache is a temporary memory space. Also, you can find a word fast. Okay, so why do we use cache? In order to support fast accesses to data, we use cache. Okay, so you can just find characteristics the characteristics of cache, like it's a temporary memory space, and it is used for fast accesses. Then why do we need a cache? So computer systems. You can find the Wikipedia for the definition of a cache. Okay, cache in real life. So I will show an analogy of a cache in our real life. So what can you see in this figure? So you can find the large number of books in a bookshelf. Also, you can find a few books on the desk. Okay, so why is this an analogy of a cache? So you can think that books books are data. Okay, so actually we can access a large amount of data. So which means we can read uh, a large amount of books. Okay, so we can access many books on bookshelf. But actually, when you study something, we can just read a, a couple of books or a single book, right? So you can find a couple of books here, okay, on the desk. Also, you can find a pile of books here. So actually, this is a locality in our real life, right? When we study, we just focus on a a single book or a couple of books on the desk. We just read a certain contents, you know, few books, so a small number of books on a desk. Why? We can reduce the access time to the content on a books, right? So we don't need to access these books. Why? Because we just focus on uh, uh, content in a single book or a couple of books on a desk. Okay, so we can think that this is a purpose of cache, right? So and then okay, we can think that the many books on a bookshelf is the main memory, right? So main memory can contain a large amount of data, and then we can access these data, right? But what's the problem? Problem is the access time. The memory latency is very high, so which means that the performance is very low. So in order to access a certain data, main memory, then we we take long time, right? So it's the same. If we want to read a certain content, or if we read a certain book, bookshelf, then we need to access this bookshelf, but it will take longer time to access the data in a bookshelf, right? So a book in a bookshelf, right? So we can move a certain book on a desk like here. Also, you can find a pile of a book right here. So even though the access time to this pile of a book can be higher than it's longer than a book on a desk here, but the access time of this book is lower than the access time to the books on a bookshelf, right? So what does that mean? We can say that this is a lower level cache. Okay. So actually, so we can observe locality, the data locality in our real life. So it means when we do something, then we just focus on a certain data, right, in our real life. And then in order to reduce the access to this data, then we can manage books. Okay, we can manage data like this. This is the add-on cache. Okay, it's a very small, but the access time is very low. And then this is the low level of cache. So we can just store a small number of books on the desk here, a pile of books. But so we can reduce the access time to these books. And then, this is a main memory. So we can access every data in main memory, but it will take time. So this is an analogy of cache. So we can understand the cache like this. Then, so this is the memory hierarchy. So where is a cache? Cache is here. Okay, so this is the register file. This is main memory, and then you can find multiple levels of cache. So like the add-on cache, level on cache, L means the level. So level on cache, level 2 cache, and then level 3 cache. Typically, a CPU includes until the level 3 cache. So if you read a CPU specification, then you can find that, Intel CPU includes level 1 cache, level 2 cache, and level 3 cache, right? So this is a cache, computer system. And then I mentioned that cache is a temporary space. It's not a main memory, right? Okay. And then actually the cache is managed by hardware, okay, not software. Also, then where is caches? Processor core. So this is the 5-stage pipeline architecture we learned in chapter 4, right? Then where is our cache? So actually you can find that, this is the register file, right? And then actually core is here, the CPU core. So this is the register file, and then cache and main memory. So main memory is here. This is memory. Then, but in chapter 4, we learned that, this is an instruction memory, right? This is the instruction memory, and then this is data memory, right? So, but, the main memory is far from a core, right? So where is our cache? So actually, these are, so there are two memories here, right? Instruction memory and data memory. So actually, in a processor architecture, these are caches. So this is the instruction memory. So actually, this is instruction cache. This is data cache. And then these caches are close to a CPU, right? Actually, you can find these caches are in a processor architecture. So these caches are level 1 caches. So L1 instruction cache and then L1 data cache. Okay. So actually, in a process architecture, instruction memory is an instruction cache, level of instruction cache, and then data cache is a data memory. Data memory is level 1 data cache, right? So then you can observe it. Oh, what is the cache? It's a temporary memory space. Okay, it's a storage space. Okay, it's temporary space. Okay, it's a temporary. And then, this is fast. So actually, when we learned about the CPU architecture, the processor architecture, we assume that the access latency, the access latency to these instruction memory and data memory is is lower than the one clock cycle, right? So it's very fast, right? So so, so which means, oh, it's fast. That's why we use caches in this process architecture. Okay, so it's just so even though we learned that all these are memories, but now so you can find that all these are caches. Okay, so then what do we need to consider? Okay, so cache is a temporary memory. So we cannot store entire data in a cache. So it is because the cache size is small. So which means we need to consider what data is held, what data is stored in the cache. So what data is need to be stored in the cache. So we learned that uh, why do we use memory hierarchy? Because we cannot use the perfect memory, but we can use memory hierarchy because our applications exhibit data locality. Then what is a data locality? Data locality represent a, a frequently used data. Which means if a data is used once, then this data will be used. So this data can be used in the near future. Also, the neighbor data. If a certain data is used, neighbor data can be used in the near future. So this is the data locality. And then, so what data is held in the cache? So answer is frequently used data, right? Because, and then this we can just estimate. We can estimate the frequently used data using actually data locality. Because so what data is held in the cache? So frequently used data. So think about this analogy. So which book is which book is placed on the desk? Frequently used. So which means that the books we are using for the current study, right? The frequently used books needs to be placed on a desk, what data is held in the cache? Frequently used. Okay. So how is data found? Then how can you know, oh, this is the data we want to use? So how can we identify data? How can we identify? So how can you identify? How can I identify you? Like, so ID, right? Student ID, right? And or so how is the data find? How can you identify data in a cache? We can use address. So what does that mean? Oh, this is the temporal space, and then the space size is small, and then we cannot store entire data. So, and then in order to identify the data in a cache, which is required, we need to also store address in order to identify data. Okay, so address. Then what data is replaced? So, and then it represents the the cache management scheme. So which means, so we cannot store entire data. So that because the cache size is small. So which means if a cache is full, right? If a cache is full, and then if we want to store additional data in a cache, then what can you do? We need to evict. We need to remove the existing data, and we can allocate a new data in a cache, right? So this is the replacement in a cache. So what data is replaced among existing data? So what data is held? So what data is need to be evicted? Is kicked out from the cache. So what data is held? Frequently used. What data is evicted or replaced? Infrequently used data, right? So actually we need to select. We need to select. Oh, we we can estimate. Oh, this data we will not use this data in the near future. Okay, so it's infrequently used. Then this data can be replaced, right? So this is the cache design questions. So you need to uh, consider these questions for designing caches. Okay, what data is held in the cache? Frequently used data, obviously. How is data found? We require addresses of data. What data is replaced? Infrequently used, right? So we can estimate, oh, this data will not be used in the near future. Okay, then this data can be evicted. so so this is the structure of a cache. So cache is also memory. Okay, then what is memory? So memory includes multiple entries, right? Multiple the memory element. So so memory includes the multiple entries, right? And then we can access a certain entry using address, right? Right. So cache is also memory, okay? So which means we can just access the cache like the data. So it's a data array, and then this data array is accessed by index. So actually for the cache memory, so instead of address, we use cache index. Okay. So it is because, so how is the data found? So we need to use the address of data, right? So in order to distinguish the address of data and the address of cache, when we mention the address of cache, then we use indexes, okay? So think like this. So actually, when we design a memory module, then this memory module includes the multiple data elements, right? So we just declare a data array, and then in order to access a certain data element, like or data entry, then we use index, right? So it's a cache is the same. Cache also has the cache is memory, right? So it's a temporary memory, right? It's a small memory. So in order to access the data in a cache, then we need to use the index of data element in a cache. Okay. So this is the data. So data in a cache. Then we want access the a certain data in a cache, like here. So actually we can store multiple data in a cache, like you can find x1, x4, like xn minus 1. So actually, what can you observe? So this is data, right? But actually, and then you can find that this is address of data, like the subscription of a subscript number. So you can think that this is the address of data. So when a certain data is stored in a cache, then the data can be stored in the any entries in a cache. So the data order in a cache is not the same to the address order of data. So how do we now know if data is present? So that's why we need to also store the address. Okay. So then if we want to access the X4, right? Then we also check the stored address in a cache, right? Then if this address is the same to the 4, then we can access this data, right? So this is how the cache works. Okay. Then when you allocate a new data, then we need to define where the data is allocated in a cache. So what does that mean? So I mentioned this is a cache, right? And then cache is a memory, so which means cache includes multiple entries. So it's a multiple space for storing data. And then let us assume that, initially the cache is empty, right? So cache is empty. And then we want to store a certain data, data X to the cache. Then how can you select the location? The location of cache that which will store this new data. So this is called the cache mapping scheme. Okay. So we need to select the location of this data in a cache. So we can apply some different cache mapping schemes, right? But so in this time, we will learn about the direct mapped cache. So when we store this data, right? And then actually I can access this data using load address, right? So when we access the data with load address, then what is required? The load address has a load instruction. Sorry. So we can access data using load instruction. Then the load instruction includes address, right? So which means when this X is fetched from the main memory, right? So the cache is the temporary memory. So we just store a certain data in a main memory to the cache for the fast accesses, right? Then this data has also address, right? Obviously. And then I mentioned that, so in order to identify the data in a cache, then address is also need to be stored in the cache. But so direct mapped cache means that, so when this data X is stored in a cache, then the part of address. So for example, oh, this address is the 0x 1004, right? Then we can use this part of address as the index of cache. So in a binary address, then we can represent that this is the 1000000000100, right? And 000. Then when we store this data to the cache, then we just use a certain field like 001, the part of address bit, this field as the index of cache. Then what does that mean? Oh, this address is so we just use these 3 bits as the index of cache, right? Index represents the index of this cache array. Then, oh, this is 001. Then this data will be stored in the cache index 001 here. So this becomes the location of data. Okay, so we can decide the index of cache from the address of data. Okay, and then this scheme is called the direct mapped cache. Direct mapped cache. Okay, the direct mapped cache means that the location is determined by address. So actually the part of address, right? And so, and then using this part of address, we can use this as the index of cache. So which means that we can determine the location of data in a cache. Then, direct mapped cache, then actually the multiple data can be mapped to the same index of cache, obviously, right? Right. So so actually, the cache size is small, so which means that the multiple data can be mapped to the same location. But in the direct mapped cache, if this part is the same, then the data which have the same address part, like 001, these data are mapped to the same index of cache. So in this example, so if this address is 001, then like the 0001, 1111, 111, 001, 00. So the data which has some 001 part in the address, then this data is stored in the same location. So this is this figure shows the concept of the direct mapped cache. Okay, so this is the cache indexes. So this is the cache, and then this is the main memory, right? So you can find, so actually the main memory address is the 5-bit, and then cache has 8 entries, right? So which means that we can use the 3 bits for cache, right? As the index of the cache, right? So which means in this example, we can use the lower 3-bit of the main memory address as the index of the cache, right? Then this memory block, and then this memory block, this memory block, this memory block. So these memory blocks are mapped to the same location, so same entry of cache. So which means if we just access these blocks using the load instruction, then these blocks are need to be mapped to the same entry of cache, because the index is the same. So this is the direct mapped cache. Okay, we just use a part of address as the index of cache. So which means we can determine the location of data which will be allocated to the cache. So then what is required? So I mentioned that in order to identify the data in a cache, right? So I mentioned that we also need to store address, right? But actually, we don't need to store the entire bits of address for the direct map to cache, right? So it is because actually the part of address is used for the index of cache. So which means if we just access this data, the cache index 001, then which means, oh, the data in this entry, this data has the 001 in the lower part of the address. So which means in the direct map to cache, based on the location, based on the index of data in a cache, then we can figure out the part of address bits, right? Obviously, right? So if the data is found in this location, then we can figure out that, oh, the lower 3 bits of this data is 001. But we need to identify this data. So which means we require the entire address bit. And then because we just know the part of address, then we don't need to store entire address bits, right? We can just store the remaining bits of address, right? So in this case, if we just store the upper 2 bits in this example, right? Like 00, 01, 10, 11, then we can identify data in a cache, right? Do you understand? So this data, in order to identify the data in a cache, we need to store entire address, but actually we just require the part of address bit. So this data is called a tag. Okay. So I mentioned that. So in order to identify data, we need to store address, but actually in the direct map to cache, we can use the part of address as the index of cache. Then we can just store the remaining address bits. So this remaining address bits is called a tag. So which means when a data is stored, when a data is allocated in a cache, then we also store data and a tag, right? So part of address for the direct map to cache. Okay, do you understand? And then why do you use, why do we need tag? Because we need to identify the data address, right? But we don't need to store entire data, entire address, right? So the part of the part of address is stored, and then this part of address is called a tag. Okay, and then also cache includes the cache flag. So cache flag represent the status of data in a cache. Okay, so we also need to store the cache flag in a cache. So for example, oh, this is the cache memory, right? And then I mentioned that initially the cache is empty. So what does that mean? This cache does not include any valid data, right? So which means, oh, this is the memory. The cache has a certain memory space, but this is just the hardware, right? So cache has the space, and then we need to figure out, oh, valid data is in the cache or not. Okay, so we need to check validity, the validity of the data in a cache entry. So it means actually each cache entry requires valid bit. Okay, so which means if this valid bit is 1, so which means that, oh, this entry includes a valid data in a cache. But if this valid bit is 0, then which means, oh, this data is invalid. So which means that, oh, this space is empty. The corresponding cache entry is empty. Okay, so we require additional flag bits for the cache entry. Okay, so in a cache, so in a cache, then we require a data space, right? So data needs to be stored in a cache. Also, we need to store tag, the part of address for identifying data. So cache also needs to store tag. Also, cache also needs to store flag bits, like valid bit, right? So tags and valid bits or cache flags need to be stored in the each entry of a cache. Okay, okay, let's see the example. Okay, so cache example. So this cache includes the 8 blocks. Okay, which means this cache includes the 8 entries, right? And then the size of a block is the 1 word. Okay, it's a 1 word. What is the word? It's the 4 byte. And then the cache mapping scheme is the direct mapped. So that's what we learned. Okay, so so because this cache has 8 blocks, then we need to use the 3 bits for cache index. So you can find the dollar sign here. So I frequently use the dollar sign for representing cache, right? Because the pronunciation is the same. So actually, cash, so it represents the money, and then actually the pronunciation is the same to the cash. So that's why actually the computer architecture, so we frequently represent cash as the dollar sign, like so L1 cash, L2 cash, like this. Okay, so I also frequently use dollar sign as cash because the pronunciation is the same, but the meaning is different, right? So we can use, because this cache includes 8 blocks, so we can use 3 bits as the cache indexes, right? So you can find the cache indexes here, right? 001, 002, 111. And then, so actually, so cache does not store the index part, right? Because we can just access the corresponding cache entry using just the index. So you can find that this is the address of cache. Okay, so and then you can find the valid bit. So this is the cache flag. Okay, and then you can find the tag space and data space. So and then this is the initial state of cache. So initially, when you just turn on your computer, then the cache does not include any data. So cache is empty. So which means that the cache, the entire data in a cache is invalid. So you can find that, oh, this is n. So it's not valid. So actually it means 0, right? So all data are invalid, right? So, and let us assume that the processor execute load instruction, the load word instruction, then word address is 22, right? So this is the hex word address. And then we can translate this word address as the binary address, like 10110. So just consider that this is the word address, not byte address, right? This is not real address, right? So this is word address, okay? So, and then, the byte address is the 4x of the word address, right? So, so load word try to access the data of word address to 2, right? Then I mentioned that when we learned about the memory hierarchy, when the load instruction is executed, then this load instruction firstly checks cache, right? So we learned about the memory hierarchy. So firstly, the CPU checks the L1 cache, right? And then if the data is not found, it's a cache miss, then the processor accesses L2 cache, the lower level cache. And then if the data is not found, it's a cache miss in L2, then the processor accesses L3 cache, right? It's a cache. So like this. And then initially, so cache is empty. So the load word accesses level 1 cache, L1 cache, or cache is empty. Then what is the event? The result of cache access is cache miss. Okay, you can find the cache miss here. Then, this is the direct mapped cache. Then what is the index of cache? So because this cache has the 8 blocks, we can use the lower 3-bit as the index of cache. So cache index is the 110. So 110 is the location which will store the fetched data. Because this load word is missed in a level 1 cache, then this load word will access the lower level cache or main memory, right? Then we can finally find the required data, the demanded data in the low level cache or main memory. Then this data is allocated to the cache. Okay, so cache miss is encountered, right? Then we cannot find the data in a cache, right? Then we can find the demanded data in a low-level cache or main memory, right? Then this data is transferred to the cache, right? Then this transferred data is stored in a cache, right? Then why? Why? Why cache stores this missed data? Because of, so I mentioned that the cache needs to store frequently used data. So which means, in the near future, this data will be used again. Then why this data is stored in a cache? Because we assume that the data exhibit uh, temporal locality. So, this data is used by an application, a program. So, but we want to access, so for example, A equal 0. A equal 0 is executed in our program, right? So which means that we want to access this data A, but this data is not found in a cache, right? So we access we load this data, right? And then we assume, we can expect that, in the near future, this data will be used, right? So the because of temporal locality, right? So if the cache miss is encountered, the cache access result is missed, then this data is fetched from the low-level cache or main memory. Then this fetched data is allocated to the cache because we can exploit, we can utilize temporal locality. Also, we can, by allocating this, then we can also exploit the spatial locality. Why? So usually the cache block size is large. So in this example, we just store the 4 byte of data in a cache, but actually, in a CPU, or in a real CPU, the cache block size is typically 64 byte. The one block size is 64 byte. So which means in a single cache block, then we can store multiple data, right? So for example, so if we just access the array data, like the 4 byte array data, like A0, A1, A2, then for this 4 byte data, we can just store the 16 element in a single cache block. So if the cache block size is 64, right? Then, we want to access this A0. Then it's a cache miss, right? Then the entire block is fetched to the cache in this case, right? Because the cache block size is 64 byte. So even though the load word instruction just access the A0, the first element of array, but and then cache miss is encountered. In this case, the entire cache block is requested to the low level cache or main memory. And then so this amount of data is allocated to the cache. Why? We want to exploit the spatial locality in this case, right? Even though this data is just missed, but the larger data, larger data block is fetched, allocated to the cache because we want to exploit the spatial locality. Do you understand? So in this example, the cache block size is 4 byte, right? It's a word. So it's a miss, and then cache block, the index of this data is 110, the lower 3 bit. So 110. So when the data is fetched from the low level cache or main memory, then data is stored in the cache entry indexed by 110. And then I mentioned that the address needs to be stored, but we don't need to store entire address, right? 10110, because we already know this address of this data is the lower 3 bit. The lower 3 bit of this data address is 110 because the index is 110. So we just store upper 2 bits as tag, right? So 10, and then it becomes the valid. It becomes valid. And then this is another load word, and then address is 26, and then the binary address is 11010. And then we can know that, oh, row 3 bit is the index. So we can check this one, but actually, when you check the 101, okay, cache index 101 here, okay, then, oh, it's invalid. So this cache entry is empty. So which means it's miss. It's a cache miss. Okay, so it's a miss, and then the request is given to the low level cache or main memory, and then data is allocated to this cache. So tag is changed to the valid, and then the index of this cache is the 101. So we need to store just the upper address bit of this data. So we just store 11 as the tag of this data. Then, the load word execute the data fetch with the address of 22, right? Then, so binary address of this load instruction is 10110, right? Then so index of this access is 110. Oh, this is the load instruction. Then first access the cache 110, right? Oh, cache has the target entry has a valid data because the valid bit is Y. Then we need to check the request data exists in the cache, right? Or not, because our cache has the valid data. Then how we can check the address of this data, but because the lower 3 bit is used as the index, we don't need to compare entire address, obviously, right? Because it's the same 110, and then this cache entry has stored the data of the lower bit of address is 110. So we don't need to compare this one, right? Already 110 is the same. Then we need to compare the upper bit as the tag, right? So we just compare this 10, and then the stored tag in a cache 10, and then we find that the tag is the same. So it's called the tag is matched. So tag is matched in this case. So which means this the data in the cache is the address of this data in this cache block is 10110, right? And then this is the same to the request address of requested data. Because the tag is matched, this is valid. So which means, this cache has the requested data. So data is found. So if the result is cache hit, right? So we can read this data quickly. Okay. So this load instruction does not need to access the low level cache or main memory because the request data is found in the cache. That is a cache hit. So we can quickly access this data from this cache. And then another load is the address is the 26, and then also the index is the 010. So we can check this array, this block, cache block. The index is 010. It's valid, and then also tag is matched, is 11. So the tag is matched. So this is hit. It's a cache hit. Then we can read the data from the cache. So this is the cache hit case. And then also you can find the additional, the load instruction like 16, 3, 16. So if 16, then binary address is the 0100. So this is the index, or it's a missed firstly. And then 3, the 011. So it's a missed. And then 16, the same. So this is the order of the load instruction. So 000. So then hit. Okay. Then this is the replacement case. The data block of cache is replaced. So the load word accesses the word address 18. Then the binary address is 10010. So this is the index of the cache, right? So this is the index of the cache, 010. Then it will check this cache block, right? So the valid bit is 1. So which means this cache block includes valid data. Or then we can compare the tag, right? So 10. So and then the tag of the existing data is 11. What does that mean? Tag is not matched. So which means this cache has the valid data, but this cache does not include the request data. Why? Because the address is different. The address of stored data is different from the address of requested data. We can check the tag, right? But tag is not matched. So what does it mean? This event is miss. It is because the request data is not found because the tag is not matched, right? Then in this case, but the problem is that the corresponding cache block includes valid data. In this case, this original data, so this existing data is evicted. It's kicked out from the cache, right? Because this data needs to be stored to this cache block because the index, so this is direct mapped cache, and then based on the index of this data, then this data needs to be stored in this block only. But this block includes the existing valid data. So in this case, the original data needs to be removed. So it's replaced. So which means that it's evicted from the cache. Then new data is allocated. Okay, so this is the cache replacement. Do you understand? So this is the cache miss because the tag is not matched. So new data needs to be allocated, but then existing data needs to be evicted from the cache. Okay, so you can find that this data is removed from the cache, and then new data is allocated. This is the cache replacement. Okay, and then so this is the miss. So we can understand the cache structure like this. Okay, so and then we can also understand how the address is mapped to the tag index or byte offset of cache. So this is the address of data. Okay, and then for the direct mapped cache, we already learned that the part of address of data is used as the index of the cache. Also, the cache block size is usually large. It's larger than 1 byte, right? So in this example, the cache block size is the 4 byte. So which means address 00211, so LSB, the low address 00211 is actually included in the same cache block, right? So a processor uses byte address, right? So 1 byte, so one address 1 represents the 1 byte of data, right? And then cache block size is usually large, right? So in this example, the cache block, a single cache block size is 4 byte. So which means a single cache block includes the address range 00211, right? So the first 2 bits, the lower address 2 bits of the 2 bits of the lower 2 bits of address as used the byte offset. So it represents the byte data in a cache block. Okay, do you understand? And then you can find the number of blocks in a cache. Okay, so you can find the index. In the index range is the 0 to 1023. So what does that mean? This cache includes the 1024 blocks, right? So in order to identify these blocks, we require 10 bits of index bit, right? 10 bits of index. So the next 10 bit will be used as the index of cache, right? And then in the address bit is an example of a 64-bit computer. Then remaining bits are used as a tag. Okay. So when the data is stored, then tag is also stored in the cache block, and then also you can find the valid bit. Okay. Then when the load instruction accesses the cache, then firstly, so we need to check the valid bit of the target cache block, and then we just check the tag is matched, tag is matched in a cache, and then if tag is matched and then it's a valid, then it's hit. So in the hit case, then we can read data from cache. Okay. So this figure shows how the data address is allocated to the cache tag, and then cache indexes and byte offset. The byte offset of the cache block. Okay. So in this example, we just assume that a single cache block size is 4 byte, but actually, as I mentioned, that the normal cache actually includes the large block. So this example shows that a single cache block size is 16 bytes, right? Then we need to use the lower 4 bit as the byte offset because the block size is 16 byte. And then if the cache size, is the same, no, actually no. And then this cache includes the 64 block, so which means we require 6 bits for cache index. So the next 6 bit is used as the index bit. Then the additional, what is it, 22? So it's 32, 31, right? The remaining bits are used as the tag of cache. Okay. So we can also use the larger block cache. Then, if we use the larger block in a cache, then we can exploit the spatial locality, right? But then what is the spatial locality? So the spatial locality means that if a certain data is accessed, then in the near future, the neighbor data will be accessed, right? So, for example, if the cache block size is 4 byte, then if the A0 is missed, then a single block will fetch A0 to A, no, 4 byte, not 4 byte, 16 byte, right? Then, A0 is missed in a cache, then this cache will fetch the array element A0 to A3, right? And then if the cache block size is 64 byte, then if the A0 is missed in a cache, then this cache will fetch A0 to A15. Okay? So what does that mean? If the cache block size is large, then a single cache block will include the more data in a cache. Then which means if the cache block size is large, then we can utilize spatial locality of data, right? So which means, so let us assume that this is the for loop. We just use the for loop, and then this for loop just access the AI, right? And then the first iteration, A0 is missed in a cache, then the 16 byte, if the cache block size is 16 byte, then this amount of data will be fetched. Then in the next iteration, A1 is hit, right? And then A2 is a hit, A3 is a hit. And then A4 will be missed. But if the cache block size is larger, it's a 64 byte, then A0 is missed, and then A1 is hit, and A2 is hit, A15 is hit. What does it mean? Because the cache block size is large, then we can increase the hit ratio in this case, right? So this is the benefit of larger cache block. Then, but if we just adjust the cache block larger, but this cache also includes the disadvantages. So if the cache size is the same, so for example, we can just calculate the size of the cache like this. The size of cache block size multiplied by number of cache blocks. Obviously, right? This is the size of cache, right? But if the cache size is fixed, right? So for example, so the cache size is 1 kilobyte, right? And then if we use the 16 byte of cache block, then this cache will include the how many? 64, right? 64 blocks, right? But for the same size of the cache, and then if the cache block size is 64, then this cache will include the 64 blocks. So what does that mean? Obviously, for the same size of the cache, if we increase the cache block size, then number of cache blocks is decreased. Obviously, right? Because the size of cache is equivalent to the number of cache block multiplied by the size of a single cache block, right? And then this is the hardware resources. So which means if we just invest the same hardware resources, and then if we just increase the cache block size, then number of cache blocks are decreased. Number of cache blocks is decreased. And then if the cache includes the fewer blocks, then it means the cache just store the fewer different data blocks. So what does that mean? So if we just increase the cache block size, then it can be better for this case, like A0. So A0, we just iteratively access the A0, A1, A2, blah, 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 blah. But if our application accesses many different data arrays, like the A array, B array, C array, D array, and then Z array, so different data arrays, many different data arrays, then if the cache includes fewer blocks, then cache performance can be degraded because the cache just includes the fewer blocks. Okay. So in this case, the miss rate can be increased. Okay. So cache miss rate or cache hit rate are highly influenced by the characteristics of applications, actually. Okay. Also, if we just increase the cache block size, then miss penalty is also increased. So we will learn about the miss penalty later, but so actually, so you can understand that miss penalty is the time for fetching a certain block, the cache block. So because the cache block size is increased, then in order to allocate this cache block, then we need to fetch more data, from the low-level cache or memory. then it will take longer time. Okay, so miss penalty can be increased. Okay, so when we consider the cache block size, then we can also consider these part, the special locality of our application, and then also the characteristics of our application, also miss penalty. Okay. Okay, so I will stop here, and then so thank you for your attention. See you in the next class. 감사합니다.